And so now we'll have the pleasure of having Hélène Morlon from not far away, from the École Normale Supérieure, and she will tell us about the mathematics of the diversification of life. So now we're talking about evolutionary issues.
Good morning. Happy birthday, Thomas. And thanks for having me here. So I'm going to be talking about the diversification of life, and I'm not going to be very original by starting by quotes from Darwin, talking about the beauty of life around us, talking about ecosystems, and so this is what he said. It's interesting to contemplate an entangled bank clothed with many plants of many kinds, with birds singing on the bushes, with various insects and so on, but these elaborately constructed forms, so different from each other and dependent on each other in so complex a manner, all have been produced by laws acting around us. So really emphasizing the complexity of ecosystems and biodiversity around us, but at the same time saying how these complexities and these different organisms all comply to similar laws, similar rules. And the next quote, also from Darwin, who said, "I have deeply regretted that I did not proceed far enough, at least to understand something of a great leading principle of mathematics." So thinking that these laws that can help us understand ecosystems and biodiversity around us can be written in the language of mathematics. So hopefully I'm going to give an illustration of this idea, showing how diversification of life can be seen as simple stochastic processes. So when we think about the diversity of species today, we can think about their diversity in terms of the number of species in given clades, and also the diversity of phenotypes that these species have. And we can try to describe the evolution of this diversity with simple stochastic processes. For example, if we can think about phenotypes such as body size as a quantitative trait evolving on a species tree phylogeny, and we hypothesize that these traits are inherited at speciation and evolve gradually during a species lifespan. So really like with a process of gradualistic evolution, then we can measure trait evolution during a species lifespan like a Brownian, or known in mathematics more like the Wiener process, so this diffusion process that we've already talked about. And again, this is a process that is useful in economics, in physics, in cosmology, and also in evolutionary biology. And so there's part of models that we develop in my group, where we build upon these types of diffusion processes to model how quantitative traits such as body size evolve on species clades, so during the evolution of groups of species. And from that, we can learn about how phenotypes evolve and how the diversity of phenotypes came to be. I'm not going to be talking too much about these types of stochastic processes here. I'm going to be talking more about how we can learn or about how the richness, species richness in a given group of species evolve throughout evolutionary history using the stochastic birth-death process. So if we model, or if we imagine the diversity of species in a given group, has a birth-death process where we start with an ancestral lineage, and these lineages have per unit time, per lineage, a rate of giving birth to a new lineage, so a rate of speciating, and a given rate of extinction. So we have this process that we see here on the left. So this is represented in mathematics by a continuous time Markov process with two types of straight and transitions. So we have births that are going to increase the states of species richness by 1, and deaths which are going to decrease the state by 1. And again, we are here with a process, a birth-death process that has applications in demography, in queuing theory, epidemiology, and also in macroevolution. So this process was first studied, or it was studied a lot in demography. That's why it's called the birth-death process, so modeling the dynamics of number of individuals in a given species. And if we note n of t, the stochastic variable that describes the number of lineages at a given time under this birth-death process with rates of birth and death that can vary through time. Kendall came up with an analytical expression for the probability distribution of this stochastic variable n, so a way to describe what's the probability after a given time t that we have little n lineages in a species group, and that's the analytical expression from which we can have some interesting mathematical results. So, for example, if we assume that the rates of speciation and extinction are constant through time, we can compute the probability that a given group of species goes extinct. And we see, for example, that this probability is going to tend towards the extinction rate divided by the speciation rate. And when we have high extinction rates, of course, approaching the speciation rate, the clade is almost certain to go extinct. And we can have a generalization of this type of conclusions in the general case where speciation and extinction rates depend on time. What we see from this is that as soon as there are extinction, the clade has a non-probability to go extinct, even if the extinction rate is rather low. And we can also find necessary and sufficient conditions for the clade to be almost certain to go extinct. The ability also to compute the probability distribution for the number of species in a species group after a given time gives us the ability to compute what the expected number of lineages at a given time. Thank you. And I will show later how this can be useful in some cases. So those are, let's say, mathematical properties that we can derive from this process and that we can study like theoretically. But then what's also interesting is that we can actually apply this very simple idealized stochastic process on actual empirical data to learn things about diversification dynamics from the data that we observe today. In particular, we are able now to reconstruct species phylogenies from molecular data. So those are, let's say, like tree of life, evolutionary tree that represent the timing and succession of divergence events in species groups, such as here in mammals, birds, amphibians, fish, and so on. We have an increasing access to this type of data, and we can adjust the type of models that I showed to this data to test hypotheses about diversification dynamics. So, for example, what we can do is knowing only like the age of a clade, so when a given clade originated, and the number of species in this clade, we have estimates for either the speciation rate, which is just going to be given by the log of the number of species in a given group divided by its age. In the absence of extinction, if we add extinction to the process, then we cannot say something independently about speciation and extinction just from this information about species richness and age, but we can estimate the net diversification rate, so speciation rate minus extinction rate, with some hypotheses on the relative extinction rate, the extinction rate divided by the speciation rate. This is a little bit technical, but for example, the type of biological question that this allows to answer is to identify a group of species. Here we have a case of an angiosperm tree of life, where we have for major clades, both the age in the x-axis and the number of species on the y-axis, and we can come up according thanks to the birth-death process with an estimate of the confidence intervals of the expected number of species given a clade age background speciation and extinction rates applied to the entire angiosperm tree of life. And we can identify those species group that have diversified especially fast, or so that are above this confidence interval, and those that are diversified pretty low. So to identify this type of the big radiations, the groups that have experienced particularly fast diversification processes. So that's what we can do, just knowing the age and species richness in a given group of species. Now, if we have a species level phylogenetic tree, so again, in these trees, we only have information, we're only using information about present-day species, their molecular sequences. Potentially, we can use few fossils to date these phylogenies, but all the extinct lineages are not represented in these phylogenies, and yet, by working on the birth death process in the 90s, some researchers had an insight that even though all the extinct lineages are absent from this type of data, we can estimate extinction rates from molecular phylogenies. And so we can see that by studying the process. So we consider, again, like this homogeneous constant rate birth death process with speciation rate as lambda and extinction rate mu. And what we can do is derive mathematically the expected number of lineages in the reconstructed phylogeny. So the reconstructed phylogeny is the phylogeny we would observe today, the one that is missing all the species that didn't leave any descendant to the present. And what we can show mathematically is that this accumulation of lineages through time, which is called the lineage through time plot, accumulation of lineages in the reconstructed phylogeny, has a slope that tends towards the net diversification rate in the ancient past and tends towards the speciation rate in the close to the present. So from that, we see that, yes, there is information that in the reconstructed phylogeny, if we look at, if a clade evolves according to this simple constant rate birth death process, we can estimate lambda from the slope of the lineage through time plot towards the present, the net diversification rate from its slope in the deep past, and then have independent estimate of speciation and extinction rates from data that doesn't contain any of the extinct lineages. Now we can do that more formally by using the principle of likelihood optimization, and that allows to then compare a bunch of different models with different hypotheses on how speciation and extinction rates might vary through time or across lineages, and so on, and to get at estimates of these parameters that are really important for the diversification of life, speciation rate, and extinction rates. So that was the intuition in the 90s, and also what was shown by studying this stochastic birth death process. And since then, there has been a lot of development building on the stochastic birth death process to construct a variety of models that allow studying how speciation rates and extinction rate vary through time across lineages, and so on. And so that's some of the work we've done in my group. I'm going to show some examples to give like more concrete idea of how this works. Here we have a phylogeny of present-day cetacean species, and we can adjust, so we can use the birth-death process to find the parameters of speciation and extinction, how they vary through time, that maximize the probability to observe this phylogeny. And we're going to find what we see here on the right. So some cases where speciation rates decline through time, cases where speciation and extinction rates are constant through time, a case here where the extinction rate increases through time. And once we have the ability to estimate these rates and how they vary through time, we can use this equation that I showed before that gives the expected number of lineages at a given time t, given the speciation and extinction rate, and we can reconstruct an estimate of how species richness evolved during the evolution of the cetacean. So here we see periods of the evolution of a group where there has been an increase in diversity in some groups, and then what we call boom and bust pattern, a decline starting around 20 million years ago for this group and 10 million years ago for this group. This is a comparison of these estimates obtained from only present-day data to the curve of species richness for the cetaceans obtained with fossil data, where we see a pretty a good agreement. The story won't be that pretty for all the groups, but just showing that these simple stochastic models can tell us something that is realistic, at least. Now, again, we can do some more work on this stochastic process and get at expressions such as the probability distribution to observe a given number of lines conditioned on things that we observe. So, for example, the number of species at present, which we are able to observe, and this is going to give us more precise estimates of the number of species in the past and of their the confidence we can have in these estimates. Here is an example on batracian, showing how on this, so here there would be this group that is more one that is that has been diversifying in the recent past, and this one, which is an old group and quite species poor. And for this kind of groups, there's always two hypotheses: has it been always a species poor groups, or was it rich at some point in history and then declined over time? So here is all said in the title. So here we found that this old and poor frog family are the remnant of a diverse past. So at least the estimates we get from these phylogenies are one where there has been quite a lot of species in this group in the past, but it declined, probably was replaced or outcompeted by the Neobatracia. Now we can actually adapt this type of processes to include some aspects of effects of past environmental changes on diversification that can be particularly interesting in the context of current environmental changes, and we can simply integrate some dependencies on the speciation and extinction rates on past environmental variables and test using the support for these types of models how realistic it is that these rates have depended on past measured environmental variables and how. So here is an application of these models on a bunch of phylogenies of tetrapods, where we compared a series of models that either where we have either constant rates of speciation and extinction, or models with rates that vary through time, models that can be diversity dependent, so which would depend on the actual number of species in the clade, or models that include a temperature dependency, meaning that the rates depend with some functional form on past measured temperature. And we found in a series of different groups, not for all of them, but for some of them, a significant support for models where temperature plays a role in modifying the rates of evolution. And we found that when this is the case, then we have a positive effect of temperature on rates of diversification, so faster diversification under periods of warm climates. As illustrated before, so the beauty of these processes is how we can employ them or use them because they model really general processes across the whole tree of life. And so moving on from cetaceans to tetrapods, we can start to be looking at this type of diversification dynamics in groups that are much more poorly known, such as the diatoms, for which we start to have a comprehensive representation of diversity coming from large-scale expeditions, such as the Tara-Ocean expedition, with diversity that is characterized using metabarcoding techniques, so using short sequences, but we can use information on some diatoms that are more better studied with more molecular sequences to construct backbone phylogenetic trees that are quite robust, on which we can graft how short reads to obtain the type of trees that we have now quite robust for mammals, birds, fish, and so on. And so if we have these types of data, then we can again use our birth-death process. Here is the case of a process with piecewise constant rates. So we assume that rates are constant between geological epochs, and we can estimate on each of these epochs if there has been a change in the speed of diversification and what change occurred. So here's an example on mammals where there is a signal of explosion of diversification after the Cretaceous mass extinction, and we see that there is a delay between the time of the extinction and the rise of the mammals. We applied the same model on diatoms and identified this shift in diversification rates about 40 million years ago. So that's when there is a transition between a warm climate and a cold climate, and diatoms are particularly well adapted to turbulent environments that occur during a cold climate. So this all makes sense. And if we look at the type of drivers that influence the diversification of diatoms before this 40 million years period, where there has been a big shift in diversification, and after this period, and we compare support for different models that of environmental dependent models where we look at the potential influence of different variables, such as variation in PCO2 concentration, carbon concentration, temperature, silica, sea level, and some curves derived from the fossil record for potential competitors or predators of diatom. What we see is before the 40 million year break, where there is a big increase in diversification, the major driver that is really like highly supported statistically in comparison to all the other drivers is a variation in CO2 concentration with a positive effect of decreasing CO2 concentration on diatom diversification, which might be linked again with this increase in polar regions and more turbulent waters. When we look at what happens after the 40 million year period, then this is much more heterogeneous with a lot of different drivers that have the biggest influence on diatom diversification, half biotic, half abiotic, and with some drivers like sea level, which is supported in many different groups of diatoms, where the effect can be either positive or negative depending on the group. So these types of results, where we see how the ecology of specific groups can really influence how past environmental changes have modified the diversification of different groups. We see how important it is to account for the heterogeneity of diversification that we can see in the tree of life. And so we can again build on the simple homogeneous birth-death process to include some heterogeneity, where now the rates are going to depend on the lineage. So here that's what is shown, where we have a process where at each speciation event new rates of diversification are drawn in probability distribution, which is going to be controlled by two parameters, one that is going to give the trend of the variation of the rate through time, and another one that gives a measure of how hereditary the rates are, if there is a lot of variation from parent lineages to daughter lineages, or only a little variation, and we can solve likelihood expressions using differential equations that allow us to fit this model to empirical data and see, for example, that's what we have here on the whole bird radiation, how rates of speciation are heterogeneous across different species group. Here we have the distribution of speciation rates across the whole bird phylogeny, and we have a distribution for specific species group, where we see here a group where diversification rates are rather constrained, but others where there is a very big heterogeneity, so a lot of variation in diversification. Having this ability to estimate rate of diversification across whole phylogenetic trees also give the ability to test the specific reason why some groups of organisms or some species might diversify faster than others. Here we have an example where we looked at the correlation between intraspecific genetic diversity and speciation rates, where we find a consistent negative relationship across mammal groups. And when we look at mammals as a whole, and can give an idea of how intraspecific processes that are going to modify genetic diversity scale up to the macroevolutionary scale and to diversification processes. So yeah, hopefully I illustrated this idea that we can look at diversification, even though we know that it's a super complex process with a lot of heterogeneity. We can look at diversification of life as a simple stochastic processes, and that really helps us understand how the diversity of life that we see around us has been generated. With this, I want to thank my collaborators and team. Thank you for listening.